The last concept that we have to cover in this unit is reflections. We've already handled translations, we've handled stretches and shrinks. We saw that translations are always adding and subtracting to somewhere. Adding and subtracting to the outside, to the y values, shifts you up and down and does exactly what you think it would. A plus goes up, a minus goes down. Adding and subtracting to the inside, because that's where the x's are, changes the x's, which means it shifts you left and right. Now, unfortunately, inside changes do the opposite of what we think they should, so adding goes left and subtracting goes right. Weird, but that's the way it works. And then we talked about stretching and shrinking. That is always multiplying by something. You're either multiplying by a number that is bigger than 1, or you're multiplying by a number that is between 0 and 1. When you multiply by a number on the outside, it's you affecting the y's, and just like the shifting, the y changes do exactly what we think they should. So multiplying by a 3 on the outside, that is stretching. Multiplying by 1/2 on the outside, that is shrinking. But just like horizontal shifts, the inside changes do the opposite we think they should. So if you see a 2x on the inside, that is not you multiplying your x's by 2. That's actually you multiplying your x's by 1/2. So that would be considered a shrink. And if you see a 1/4 x, I know that looks like you're dividing your x's by 4, but you're not. That is actually a horizontal stretch of factor 4, once again using the reciprocal. All that's left is reflections. And for IB purposes, we'll only talk about reflecting over 2 things. One of them is the x-axis, and the other one is the y-axis. We've already talked about reflecting over the line y equals x. That's inverses. That's technically 2 transformations. Kinda. But I digress. The point is, we are only going to reflect over the x-axis or the y-axis. Now, I know it's kind of counterintuitive, but when you reflect over the x-axis, you've changed your y's. So that would be changing the outside of your equation, specifically from positive y's to negative y's. So negative in the front. If you reflect over the y-axis, though, that's a left and right motion, which means you're changing your x's, literally from the positive x's to the negative x's. So negative sign on the outside, reflect over x. Negative sign on the inside, reflect over y. And if you struggle to remember that, the thing that I do for my Algebra 2 students is I draw this cheesy little picture, and I go, all right, well, imagine that your entire function existed here, where there's positive x's and there's positive y's. If you go down to here, did your x's change or your y's change? And you would say the y's changed. So the negative sign must have been on the outside. And then by the same logic, if I go to the left, if I take that black circle and go to the left, now my x's have changed, not my y's. So the outside should be unaffected. I went from quadrant 1 where there was positive x's to quadrant 2 where there's negative x's. And I think that little picture helps. I mean, I really think it does. If you've already got it mastered, fine. But that's all we're going to be doing today, reflecting. The result, algebraically, that these reflections have is they multiply values by -1. So reflecting over the x-axis, that means literally multiply your y's by -1. Reflecting over the y-axis means literally multiply your x's by -1. And do you know how much practice it takes to say all those things without screwing up and saying the wrong letter or the wrong axis? It takes a lot of practice. Nobody's impressed. That's okay. All right, so we have x minus 1 squared. We're going to sketch it, and then we are going to reflect it over both axes. So let's draw the original. Its vertex is going to be at 1, 0. Should look like that. Boom. And let's color code this bad boy. We'll do this one in red, and we'll do this one in green, like that. So let's do the red one first. The red one says to reflect over the y-axis because it says make your x's negative. What that does is it takes every x value that our blue curve had, and it just changes the sign on that x value. So the vertex, which used to be a positive 1 on the x-axis, is now at -1 on the x-axis. Now, I could cheese it a little bit and just go, oh, okay, well, it does this, and then that, But that just looks like I shifted the thing, doesn't it? That looks like I shifted it. So the challenge is then, how do I show that I reflected it? How about a t-table again? So our blue curve, f of x, I'm only going to use 3 points because I'm trying to be lazy here. Vertex was at 1, 0. It had a point at 0, 1, and a point at 2, 1. When we reflected over the y-axis, I ended up with the red curve. And what that tells me to do is change the values of my x's. Don't touch the y's. So the y's untouched, but the x's become that. And then, of course, I've already plotted those points and connected them. But if you do it with a table of values, you can easily see, oh, yeah, that wasn't a shift. How do I know it wasn't a shift? Because if you look from x to x, they didn't all go the same distance in the same direction. That's how you'd recognize a shift on the table. Every one of the values would have been affected the exact same way with an addition or a subtraction. So that's how we recognize it as not a shift. Does that make sense, what I said? Okay, just make sure. The green curve. Hey, you know what? This time I'll do the points tree before I plot the dots. Let's do negative f of x. That means only the y's will be affected. Change the sign of the y's. X is untouched. Change the symbol on the y's. -1, 0, -1. Booyah. And then plot the dots. 0, -1. 1, 0. 2, -1. Whee! There you go. Now, I know none of you are surprised by these images because it's simple reflections. I know that. But my point is, were you ever shown the algebra, the point trees? My Algebra 2 students, when I teach them transformations, I actually show them 2 different point trees and then tell them to tell me what transformation occurred. Just by looking at the values, you should be able to see, did they all get added to, subtracted to, did I change the sign, or did I multiply them all by something? You should be able to tell me the transformations just by looking at the points. So when I teach Algebra 2 and I give them an image of 2 different graphs and I say, tell me the transformation that occurred, on that graph, I also put the point trees of the points they should be paying attention to. So if they're geometry style people, they look at the pictures and they can tell you what the transformation is. And if they're algebra people, like me, they look at the tables and see how the values were affected. Again, if I hadn't listed out the blue table and the red table, if I had just had the blue curve and the red curve, you could have just as easily told me that that was a shift left of 2 units. But the table shows you that's not what it was. No, just me. I don't think it's just me, though. Sir?
So the end result is the same?
It looks the same.
The numbers aren't that way.
It looks the same like the end result, but algebraically it was not the same result.
Yeah.
How we get to an answer matters, right?
Yeah.
Okay.
You're right.
Yeah. So here I've got the exact same piecewise weird thing that I gave you 2 days ago. And look at this. I've asked you to sketch the graph of 2f of -2x minus 1. There is no way you're pulling that off in your head. Not possible. I mean, maybe, you know what, I'm not going to say impossible. I'm going to say, if you can do that, can you please go buy me a lottery ticket? Because, wow, you can see some things that I can't. Because that is 1, 2, 3, 4 transformations. 2 vertical transformations, 2 horizontal transformations. Honestly, I have no clue what this thing is going to look like. Really, I'm telling you. Look, I'm not holding the notes right now in my hands. I don't know what this thing looks like. Yeah, he's looking for them.
Don't worry
Oh.
about it.
What was he doing? Well, anyway, so what I'm going to do is I'm going to make a point tree for this red curve, image curve, whatever. And then I'm going to affect its 1, 2, 3, 4 points according to those 4 transformations. I really have no clue what they're going to be. So here's my point tree for f of x. Always read your curves from left to right. So negative 2, 0, 0, 2, and then 2, negative 2, and 4, negative 2. Cool. I'm way over here because I'm out of, you know what? Nah, I'm darn near out of horizontal space. So I'll come over here and I'll do 2f of negative 2x minus 1. And we know there's still going to be 4 points. Let's do the y's first. I have 2 outside changes. I have a 2 on the front, which is multiplication, and I have a minus 1 at the back. Which operation has to happen first? Multiplication, because of PEMDAS, right? So for my y values, I'm literally going to double them and subtract 1. So 0 doubled minus 1, 2 doubled minus 1, negative 2 doubled minus 1, be careful, it's negative 5, and, oh, stays the same. There you go. I didn't know that's what those y values are going to be. I needed the point tree. I needed it. Now the x's. We were very, very lucky here because the 2x transformations are both multiplications. So it doesn't matter which one you say you do first. In fact, you could perform them at the exact same time because they're both multiplications. But what if they weren't both multiplications? What if there was one multiplication and let's just say an addition? Which one would you have had to done first? No, the addition happens first. Why? It's not kind of, but transformation-wise. How about we use the words that I've been using? Because inside changes are opposite. You see, horizontal transformations, things on the x, do the exact opposite of what we think they should do. So if I show you on the inside a 2x minus 1, you have to follow PEMDAS in reverse order to pull it off. And I could show you why, or you could just believe me because how many times have you seen the transformations on the inside being exactly the opposite of what you'd expected? Outside transformations do exactly what we think they should, so they follow PEMDAS. Inside transformations do the opposite of what we think we should. They follow SADMEP. But again, we got lucky. I'm multiplying by 2 things. The negative sign says you're changing the signs on the x's. What is that 2 telling me to do? I'm sorry, say it louder. It's telling you to divide by 2. Because remember, the inside multiplication has the opposite effect is what it looks like. So it looks like you're multiplying by 2. No. You're multiplying by 1/2, which is the same thing as dividing by 2. So what I'm going to do is I'm going to multiply all of my x's by negative 1/2. 1, 0, negative 1, negative 2. What's the question, Krill?
So you have that negative 2 over there inside near the x, right?
Yes. Oh, you want to know why the reflection doesn't follow the opposite rule?
No, I want to know if I put a 1/2 outside the parentheses, would that be the same thing?
A 1/2 on the outside of the parentheses is a vertical shrink of factor 1/2.
Yeah.
But it's not the same thing as stretching an object left and right. For example, I take a can.
Okay, but here's the question. Would the graph look the same?
No.
No?
No.
Interesting. Okay, why?
Well, it just wouldn't. Well, I mean, let's look at the graph you're looking at right now.
Okay, but
If we just
what that 2 is doing is dividing by 2, right?
it's dividing the
X out.
x's by 2. That means that the object is going to come closer to the y-axis. But if you made it shorter, or if you made it taller, I should say, if you make it taller, is it going to force the points to come closer to the y-axis?
No.
No.
Just be further from the x-axis.
They're just going to get further from the x-axis, which means its width has been unaffected. Will it have the illusion of being skinnier? Of course it will, but it's an illusion. That's because it got taller. Why do you think women wear high heels?
There's actually theory.
Well, I'm telling you right now. Women wear high heels, or used to, I'm not saying all the time, this is not meant to be a misogynistic thing, but high heels were kind of created because, well, height, 1, nice legs, and 2, the taller you are, the less wide you look. No, the statement that I'm making. Hey, ladies, Do you ever wear a bunch of horizontal stripes?
No,
Why?
because it makes you look fat.
Oh, because it makes you look fat. Because it gives the illusion of stretching you to the left and right. Yeah, well, I mean, who doesn't, right? But the point is I'm going to be real right now. How many horizontal stripes do you see me wear the whole shirt be horizontal stripes? Never. No, I said the whole shirt be horizontal stripes. Never. Because it makes you look fat. Now, vertical stripes. Now, vertical stripes. I need the ab stripes, you know? Yeah.
Do women wear vertical stripes to make themselves look taller?
They could.
Sometimes.
Yeah, like pants, yeah, like pinstripes and stuff, yeah.
Not really on shorts, though.
Yeah, not shirts.
Yeah, that sounds good.
Yeah. But you know where you do see stripes on women's shirts?
Oh, where?
Around the bust line. Around the bust line. Here. Plotting my points. 1, -1, 0, 3, -1, -5, -2, -5. So here's the image. Skinny. There you go. But I'm not just making that up, am I?
No.
I mean,
Is that why you're wearing them?
yes. It does, but it has the same illusion for guys as it does for women. It makes it look like you have a bigger chest. I actually just like the shirt. It was cheap. I got it for like $7.
There you go.
Yeah. I don't buy full price clothing. You kidding me? I'm a teacher. All my stuff comes off of the clearance rack. Dirt cheap. Okay, this shirt normally is like a $50 shirt. I bought it for $7.
Is that like a public shirt?
No, it's a polo. It's actually Polo brand. Yeah, like $7 for a Polo brand shirt. Yeah, that's what I like. And I like polos, like the style, and I like dry fit. But I'm not paying $50 for a shirt. You kidding me? I can get 5 shirts for that. Huh? I try. Okay, so last question. Last question, guys. I'm telling you 2,6 is on your curve. Whatever your curve is, 2,6 is on it. I want to know where the image lands after those 1, 2, 3, 4 transformations. Luckily, there was a single transformation on the x's. So what am I going to do to my x values? You're going to multiply by 5. So the x image will be at 10. Now we just have to figure out where the y image went. You're just going to follow the order of operations. You're going to multiply by -3, and then you're going to add 8. So you do 6 times -3. That's -18. Plus 8, -10. And that is where A prime will land. Look how much easier transformations are algebraically than they are geometrically. I will now drop the pin like it's the mic.